Okay, so then we will start, even that there are, I will still continue replying few emails saying that there are problems with the passwords, but we can definitely get started. So good morning, everyone, and welcome to the FCAI Machine Learning Coffee Seminar again. And today we will have a presentation by Professor Jaakko Peltonen from Tampere University. And he will be talking about steering distortions to preserve classes and neighbors in supervised dimensionality reduction. And Professor Peltonen's presentation will be in two parts. So if you have questions during the presentation, please write those into the chat, and then I will ask the questions and open the floor in between the two parts. And then, of course, at the end, we will have an open discussion part again. But so please, the floor is yours.
Thank you and good morning, everyone. So indeed, today I'm basically giving two talks, so you're getting two for the price of one. Well, both of them are free, so 2 times 0 is still 0, but anyway, you are getting two. So the first name is actually just part 1, so the steering distortions to preserve classes and neighbors in supervised dimensional reduction. That's part 1 of the talk. The other one is called Probabilistic Dynamic Non-Negative Group Factor Model for Multi-Source Text Mining. So both of them are about exploring data in different ways, but they are otherwise fairly different talks. So we'll basically get started right away. So just briefly, I am a professor indeed at Tampere University. I'm a professor of statistics and data analysis. So I'm all into those probabilistic approaches to do fancy data analytics tasks. And we are a very welcoming place, and I have a research group there called Statistical Machine Learning and Exploratory Data Analysis, which makes SMILE as the abbreviation. So if you have any interest in what you hear today, then I look forward to your questions and contacts later on. Let's get started with the first part. So this is basically me telling about our NeurIPS paper from 2020. So my thanks to all of my great co-authors who are listed there at the bottom of the page. And it's an open access paper, so you can get all the details later on if you like. So this is about dimensional reduction and visualization of data. And basically, dimensional reduction, or DR for short, is a bunch of techniques that all aim to map high dimensional data sets to a lower dimensional space, which we often call an embedding space. And that's something that's useful for many things. It's something that people need for automated later processing, for making a better feature space for things like classification or clustering or whatever. But it's also very useful for human analysts. Basically, it helps them to look at data better when the data is lower dimensional. You can do visualizations and all kinds of exploration in that way as well. So usually these dimensional reduction approaches, they are based on preserving a kind of similarity measure between data points. And we'll be talking about that in a moment. So, but before we go to the detail, I want to mention that one problem in these approaches is that basically you are reducing the dimensionality. So you shouldn't expect the low dimensional space to be a perfect representation of your original high dimensional data. No, it's going to contain distortions. And the problem is that when things are entirely unsupervised, it's hard to know which of those distortions would be important to avoid, which of the data features would be important to preserve. So one potential solution to this is supervised dimensional reduction. So this means that you have available some kind of annotation, can be, for example, category labels for your data points. And this is what we are focusing on today. So this kind of annotation can be used to guide the embedding. The idea is that you would like to avoid those distortions that would worsen the separation between your categories, at least worsen it from what it was in the original data space. So that's one problem and a potential solution to that, or a solution approach. But there's another problem. There are supervised methods for dimensional reduction, but often these supervised methods, they kind of become too extreme. They emphasize class separation, but at the cost of then causing distortions in the neighborhood structure. On the other hand, these unsupervised methods, they do try to preserve the neighborhood structure as well as possible, but they mix these categories of data. So we are going to be proposing a method called class nerve, which can preserve both neighbor structure and have good class separation. So it can preserve, precisely speaking, the neighborhood structure and preserve the class separation. I'll come to that in a moment. So we'll come to the details in just a moment, but I want to show an example of what this would practically look like. And here is a toy dataset with 3 Gaussian clusters here on the left. And one of the clusters is just composed of one class, it's pure blue. There's another one where there exists inside the cluster a linear separation between 2 categories, blue and orange. And then there is another one where there's just completely mixed 2 categories, purple and green. So what happens when we try some of our favorite dimensional reduction approaches on this kind of data? Well, here is one of the currently very popular approaches, TSNE, T-distributed stochastic neighbor embedding. That's an unsupervised method. And you can see that the result, the 2D embedding, preserves clusters fairly well, but it ignores the classes. So the end result is that these orange and blue in the bottom cluster, which were originally linearly separated, they become overlapping, right? Now, on the other hand, here is a supervised method called SUMAP. I won't go into the detail. So that method seems to split all of these categories apart. So in particular, notice that it splits apart the orange blue cluster. Maybe, I don't know which of the blue is the one, maybe it's these 2, but it also splits apart the purple and green cluster. So it does this to force the class separation, but as you can see, it's misleading. The purple and the green were completely mixed together. The orange and the blue were right next to each other. It's misleading about the original spatial adjacency of the classes. Now, here on the right, by the way, I don't know, I hope you can see this. On my screen, this is partly hidden by the people's faces, but I hope you can see it. So anyway, the class nerve visualization is able to better preserve both the structure of the data as 3 clusters, as well as show the proper adjacency of the classes within those clusters. So this is what we are aiming for. Now let's see how we do it. Now, a little bit of history. Many successful methods for dimensional reduction are based on the concept of neighbor embedding. There are others, but I'm talking about that now in particular. So methods like stochastic neighbor embedding, what they do is that they define distributions of neighbors in a high dimensional space and in a low dimensional space. Basically, if 2 data points are very close by, then one of the data points has a very high probability of being a neighbor of the other one. The mathematics look like this. There's a distance-based definition normalized so that probability is sum to 1, one in the high dimensional space, another in the low dimensional space, and then methods like these, they minimize a KL, a Kalbi-Klape divergence between the high and low dimensional neighbor distributions. Now, the TNSC version is similar, but there's some minor differences that I won't go into. Now, recently, there's been interest in this framework called the Neighborhood Retrieval Visualizer. It's proposed already some time ago, and it's a very nice framework that shows that this thing that I just mentioned is actually just part of a larger task to maximize the information retrieval performance of retrieving neighbors from the embedding. And what that means is that you think of the positions of data points in an embedding, like a visualization, as a mechanism for retrieval, like reach out and grab a bunch of points and then see what you got. How good was that retrieval compared to the original space? So in that kind of information retrieval mechanism, you should minimize both misses and false neighbors, two different kinds of errors. Another way to say it is that you want to maximize both recall and precision, and you can set an appropriate trade-off between them. So the NERV method is something that uses two kinds of Kalb-Lab divergences, averaged with a trade-off parameter like this. So there are two different ways of comparing the high and low dimensional data neighborhood distributions. Now, the SNE, stochastic neighbor embedding, and TSNE approaches, they only took one part of this formalism, or they were aware of just one part of this formalism. So they only minimized misses, whereas NERV takes into account both kinds of errors. So this is what we are starting from. But this is unsupervised. Now, we want to take class information into account, and we aim for an embedding that is going to preserve both neighborhood structure and class separation. So the proposal here is that a good embedding with class information taken into account should not artificially separate points that are within the same class, or it should not artificially cluster together points that are in different classes. So this means that we're not just treating all misses and all false neighbors equally. We want to penalize more these within class missed neighbors and between class false neighbors. So how do we do that then? Well, among those neighbors that we just looked at, those neighbor distributions, some of those neighbors are coming from the same class as the point at the center of a neighborhood. Some of them are coming from different classes. So let's talk about these separately. So we're going to separate the divergences so that we will have one set of divergences between the high and low dimensional probabilities of same class neighbors, and another set of divergences between high and low dimensional probabilities of different class neighbors. And we are then going to have two trade-off parameters. One parameter within class and another parameter between class. Now, since we are working then between only part of the probabilities in neighborhood distribution, the part that is within a class and the part that is between the class, we can't use scale divergences because scale is only defined for distributions that sum to 1. So to ensure that we have a nicely defined positive measure, we are going to use another type of divergences called Bregman divergences. So this is what it looks like. So the class NERV probability distributions are included in divergences that are Bregman divergences here, so that the total cost is basically sums of 4 types of terms. And the first row here is the penalization of within class missed and false neighbors. So this here means within class. And this is the penalization between class missed and false neighbors. So this here means between class. Now, if you want to know the detail of what those Bregman divergences look like, so this is what they actually look like. So they're not very complicated. They look very similar to KL divergences, but with a couple of extra terms, right? So nothing to worry about. Now, this kind of method with these two trade-off parameters becomes supervised if this penalization of within class false neighbors and between class within class missed neighbors and between class false neighbors, if that penalization is bigger than for the other distortions. And that basically just means that if this parameter is greater than this other one. So in that case, we are trying to avoid splitting existing classes, and we are trying to avoid mixing classes that should not be mixed, so class overlap. Now, in the special case where these parameters have the same value, then this actually reduces to the neighbor retrieval visualizer method. In this case, also the Bregman divergences, they turn into KL divergences. So this is the basic idea here. We just kind of nicely separate this neighborhood information into within and between class terms, and then we emphasize the important parts more than the less important parts to us. So when we have this kind of cost function, we just obtain the embedding by minimizing this stress with respect to the coordinates of the embedded points in the embedding space. And we do this by an optimization approach, which involves a multi-scale approach, and there's a quasi-Newton BFGS algorithm in there as well. You can check the details. So the current implementation that we used has an O(n)² complexity, but just like many other methods, the tree-based acceleration techniques could reduce this to a nice O(n) log n complexity. Now, let's take a look at how this then actually works. Before we get started, I have to mention about the quality indicators that we will use. So commonly used indicators, trustworthiness and continuity, are adopted here. Basically, what they mean is that in trustworthiness, you take the set of false neighbors, and for each false neighbor, that means that it is in the high dimensional space, it is further off than where it ended. So this is checking that how far apart should it have been. So this is measuring the severity of the false neighbors. Continuity is going over the missed neighbors, and it is checking that, okay, in the low dimensional space, it is further off than it should have been. So how far off was it? So these are very typical measures of performance, and these are unsupervised. So now we are going to also here introduce class-aware measures. So this is basically just trustworthiness restricted to the between class relations and continuity restricted to within class relations. So there was a question in the chat. I'm going to answer them at the end of the talk, okay? So these class-aware indicators, so they are basically just considering the same idea, but just we don't consider the set of all false neighbors, just the false between class neighbors, and not all misses, but just the misses within class, right? So because these only account for part of the distortions, the value of these class-aware trustworthiness and continuity, they will always be bigger than the unsupervised versions. So they can give you one, even if there are some remaining distortions, as long as those remaining distortions don't affect the between class trustworthiness and within class continuity, right? So this is just checking that part of the distortions that we are interested in, okay? So now I want to also mention that often people use also for supervised techniques like accuracy of a classifier, like leave one out KNN in the embedding space. That's okay when you are trying to do classification, but it doesn't really consider neighborhood preservation at all. So we have in the paper a supplementary material with lots of KNN results. So check that. I'm not focusing on the KNN here as much. So we are going to compare our approach to a bunch of unsupervised methods. Here's a list, and a bunch of supervised methods, and basically 3 data sets. And let's see how much I have time to talk about them. But one of them is a toy data set where we have data on a sphere surface, and the classes are just the hemispheres of the sphere, right? So then we have spoken letters, letter classes, and handwritten digits, digit classes, right? So in the beginning, let's take a look at the globe data. So here we are just showing our method now, and we are showing how you can use these trade-off parameters to affect the result. So here you see 2 axes. One of them is basically the average of the two trade-off parameters, so that you can think of as a precision recall trade-off. The other one is the difference between those parameters, which is basically the amount of supervision. So here, the higher you go, the more supervision, and here, the more to the right you go, the less you want missed neighbors. And here on the left, you want less false neighbors. And basically, the takeaway from this visualization is that on this globe data, the method is doing very reasonable things. The trade-offs are performing their intended job. So when you have few missed neighbors and low supervision, then you basically end up with something that has class overlap, but not a lot of class not a lot of missed neighbors. And here on the other hand, you have some torn apart classes but not false neighbors. And with the supervision, you end up with this kind of solution, which also looks quite nice. And then here on the right, you see indicators. There is then nearest neighbor accuracy. You can see that it grows here with the supervision added. And then here are the within class continuity, between class trustworthiness, and then the unsupervised continuity and trustworthiness. And basically the takeaway here is that they all perform as expected. So the construction of the method works, right? But how does this compare to other methods? Well, here are a few other supervised methods here. So out of these, I could mention, well, I don't show all the methods. Actually, I guess I could. So class nerve preserved the linear separability and adjacency of the classes quite nicely. We just saw it on the last slide. So from the other methods, also another method called ClassiMap and NCA does so nicely, but these other two, SISOMAP and SUMAP, have problems. SISOMAP falsely creates a class overlap. SUMAP splits the classes apart when they really should not be split apart. So let's take a look at another data set soon, but first I want to mention that, of course, we can also quantitatively show that what we just talked about is the case. So here are the quantitative curves of trustworthiness versus continuity, and then these class-aware trustworthiness and continuity, and the same, this for unsupervised comparisons, this for supervised comparisons. And basically the conclusion is that we get similar levels of structure preservation as the unsupervised techniques as the best of them, and higher trustworthiness in general. And we preserve the categories far better against unsupervised methods. And for the supervised methods, we basically do much better in structure preservation, and we also do better in class preservation than many other methods. So quite nice results on this artificial data. Here's a real data. So this is the spoken letter data, and these are some example embeddings. And just quickly showing some takeaways here. So the NCA method overlaps classes. SUMAP and SISOMAP, they over-separate the classes. So they ignore places where the letters actually should have overlap. So this is artificially showing overly large separation. ClassiMap here, it's okay, but it fails to represent some groups. Nerve is unsupervised, so it preserves groups surprisingly well, but it still can artificially increase the overlap. And class nerve here is basically a great solution. So it's a trustworthy representation of the classes and shows confusion where confusion should exist, but keeps others separated as they actually are. And in terms of the quantitative measures here, so ClassNerve is better than the supervised techniques for the structure preservation, and it's better than the unsupervised techniques for class preservation. And then the opposite indicators, it's comparable. So here we are better than the state of the art here as well, and here we are about the same as the state of the art. And then finally, I'm not going to show everything about the digits data, but one thing we tried was just a brief check that, okay, what happens since we're using class annotation? What happens if we just replace that by some random noise class annotation, right? So just some scrambled classes. So does this break our method? It turns out that no, it does not. So in that case, we still basically preserve the structure pretty much nicely as we should. So it's kind of safe to use in that sense. So now we come to the summary of this first part. So we have a neighborhood embedding-based dimensional reduction approach that allows you to control class and neighbor preservation in low dimensional embeddings. So you can separately consider these within class and between class misses and false neighbors, and you can put supervision to avoid specifically the within class miss neighbors and between class false neighbors. We also had these continuity and trustworthiness indicator versions that are class aware, and we got good performance. That's the end of the first part. Now, maybe
Yes.
time is a little bit short, but maybe we can take one question or something.
Yeah, there was the question in chat, so I can read it aloud, so you can then reply. So Jörg Tiedemann is asking, could class nerve be extended to multitask supervision?
Meaning classes that are where you have multiple classes along different classification styles for each data point. So I believe that it could, because basically the cost functions that we use, there is a term for preserving one type of or avoiding one type of class-aware error and another type of class-aware error. So you could certainly stack them together, just add one for the one type of classification that you are using, one for the other type of classification that you are using, and so on. So that would be a fairly straightforward way to do exactly that. I'm sure that there could be other ways, but that's at least something that's immediately apparent.
Okay, great, thank you.
All right, I guess we can then move to the second part.
Yes, please, yeah.
And that's about a method for modeling text from multiple data sources over time. So again, thank you to all my co-authors. This is from a CIKM last year. And I'm not going to read the title, I already did that. So basically, we're talking about approaches for non-negative matrix factorization. That's a popular technique for modeling data in matrix form, when you also expect the data and the factors to be non-negative. So there are a bunch of methods proposed. One of them is, for example, Bayesian group factor analysis. And the basic idea is that you have a matrix, you try to factorize it like this into factor contents and factor loadings, right? So the problem is that most of the models that exist cannot flexibly take into account the scenario where you actually have multiple matrices over both different kinds of data sources and then time. So you may have matrices occurring over different data sources and over time. And some methods may have a restriction to integer data only. So we're going to introduce a method that's based on a Gaussian process latent variable model, and it can model non-negative data from multiple sources, and it's going to have flexible dynamics. It's a hierarchical latent variable approach, and we are going to model, in addition to the matrices, we're going to model a bunch of latent variables and their dependencies between topics, between sources, as well as the temporal evolution. And an example that I'm going to be using for part of the terminology is having text from multiple sources. That could be, for example, documents from multiple social media over time, right? So basically, the model structure is starting from the data format. So you have a temporal sequence of matrices, and each matrix is a combination of several text sources, and you want to factorize them like I just showed. You want to factorize each of them, and now this topic content and the prevalence, they could both be different over time, right? So here's a picture of what that might look like. So you have a common vocabulary across the sources, but then different occurrences over sources, and you factor into content and prevalence, and these, I call them topics here now. So these topics, some of them could end up occurring over multiple sources. Some of them could end up being restricted to a single source. So they would be specific to a source. And this can change over time which things exist. So we are going to be working with a really large and scary looking hierarchical model. So this is what it looks like, but don't worry, we'll go over it in parts. So let's start from the observed data. So here we have the observed data, and we basically have just a truncated Gaussian likelihood where we loop over the documents and then the vocabulary terms, so all the entries in the matrix. And then we have a truncated Gaussian here, where the mean of that Gaussian is depending on an inner product between the topic content vector and the topic prevalence vector. So for this particular vocabulary term, and then this topic prevalence vector, and there's some noise added on top. So that's nothing very complicated. But then let's look at how these prevalences and content come to be. Let's look at content first. So here we have the content vector. So for topic K at time t, the content vector is going to be derived as a softmax of latent variables, which we call etas, right? And these etas, they will have a flexible model of dynamics. So these etas, we have a vector of, for a particular vocabulary term n, we have a vector of the etas over all topics and over all time slices. And this is then drawn from a Gaussian distribution with whose covariance matrix we'll talk about in a moment. So this is the basic idea here. So we have a GPLVM-based model here. And then if we look the other way around, if we look at the topic prevalence here, then the topic prevalence for topic K in document D from source M at time T is drawn from a truncated Gaussian where the variance is controlled by these sparsity parameters alphas, right? And these sparsity parameters, here we have for a particular topic K, we have over all time slices, and then over all sources, we have again a GPLVM-based model for the dynamics. So basically, it just looks like a bunch of Gaussians, but we should talk about how we actually get these covariance matrices then. So let's come to that. So let's go back to the topic content for a moment. So the covariance matrix here is basically noise plus a kernel matrix. And this kernel matrix is composed of two parts. There is one part that is active only within the same topic. So this delta ensures that. So that's what we call a within topic consistency. And this here is actually just the RBF kernel. And this other part is the topic-topic interaction. So what you have there is a fade off over time here. And then this thing here, which is basically saying that how much does this topic at this time like to interact? So it's basically tendencies that are topic specific to correlate with other topics. So each topic has such a thing. So for a topic, we have a vector of those tendency values, and those vectors are drawn from a Gaussian process. And that Gaussian process has this kind of covariance matrix, which in turn comes from an RBF kernel. So that's it for the topic content. And actually, the situation with the topic prevalence is kind of a mirror image. So again, we have a covariance matrix that's composed of a kernel and noise. The kernel is divided into a within source consistency now, and then a source interaction where there is a fade off over time, and then these tendencies to interact, where these interaction tendency or correlation tendency vectors, they are drawn from a GP, and the covariance matrix there is just basically noise plus an RBF kernel. So this is the basic model structure. Now, we then derive, I won't go into the details of that, but we derive a variational EM inference algorithm for that. Basically, these important latent variables, they are obtained via Laplace's method. This matrix can be actually obtained analytically via a conjugacy, and then these correlation tendency vectors, they are obtained via, well, an approach that I just referred to another publication. You can check it from there, and then we use also point estimation in parts there. So we just repeat this for a bunch of iterations, and then we have a result. So let's come to comparison. So we basically first take some simulated data. Oh, this doesn't mean anything. I just accidentally left there. Don't worry. So we just take some simulated data and we do two evaluations. We either interpolate so that we leave out one of the time slices and we completely try to predict its content based on the other time slices. The other possibility is a partial article case. So we have documents in every time slice. We leave 90% of them out, 90% of each document, the text content, we leave 90% out. And so we use 10% for training and predict the remaining 90% of the content of each document. This is like using an abstract to predict the rest of the content of an article. And we use root mean square error and compare to these methods here. So there's dynamic topic models, there's GFA, there's a version of GFA with a non-negativity correction. That's a very simple thing we did. And then there's another method called JPP. Here's what it looks like. On this simulated data, we have basically RMSE, so smaller bars are better. And this here is our method, and it's the best, basically. And then among the rest of the methods, there is different variations. So you can see that, well, there is certainly differences between the other methods, but they all have their issues. Now, we also had a real case study with news and social media from Finnish sources. So Helsingin Sanomat, Finnish Twitter, and a Finnish conversation forum from different months in 2011, 2012. And here also, we first did this quantitative comparison. So again, these partial article and interpolation cases, and we show that we really do massively better than the other methods on this real data, much smaller RMSE. And of course, then we can inspect what the topics are like and how they vary across time and across these different sources. So this here is the variance of a particular topic across these three sources and over months. And this is the content of that topic, how it varies over time, because both the prevalence and the content vary over time. And these make some nice sense. I don't have time to go into the details. There's another topic where we also did the same kind of inspection, and you can see also that we are able to model this variation across time and sources, as well as how the content evolves. So we introduce now a model, a probabilistic NMF-based model. We call it DNB-GFA, which flexibly models dynamics across these multiple data sources or domains and across time slices. We have a novel formalism or a novel structure with a softmax and GP prior, and basically otherwise a novel hierarchical structure, which is a nice solution to address these temporal dynamics in multiple sources. Because we have this hierarchical structure, we can easily incorporate all kinds of prior knowledge there if we like, and practically we can do better generalization than comparable models in the results that I showed. And this is not just for text. You can use this for any kind of non-negative matrices where you have multiple sources and temporal dynamics. And this brings me to the end of my second part and my talk.
So great, thank you. So now the floor is open for questions. So are there questions coming from the audience? So you can either write them into the chat or then ask aloud by opening your mic.
Please feel free to ask about both parts, actually, if you like. So no need to just restrict to part 2.
So Saifudin, would you like to ask? I noticed you opened your mic. Please go ahead. So, sorry, the sound is not, we can't hear you. Can you check the mic?
Now you can hear me?
Better, yeah.
Yeah, get not sharing. Saifuddin and
So, sorry, the sound is again going away. So
it's garbled. Maybe you could try speaking very close to the microphone. That sometimes helps.
Okay, can you hear me now?
Yes.
Again, better, yeah.
Okay, get knowledge sharing session and get presentation. I would like to ask respected presenter, that do you have any plan in future to justify your regarding the second talk? Actually, I'm talking. Do you have any plan in future to justify your proposed work with by experimenting with other evaluation metrics? So far, if I'm not mistaken, you justified your proposed work with root mean square error, if I'm not mistaken. So do you have any plan in future to justify your work with more evaluation metrics?
Sure, there could be all kinds of metrics applied to different kinds of data. It's sometimes data specific that what kinds of metrics are applicable. If you're working with text data, for example, then you can interpret our results as topics. I use that terminology, but it's not, it's kind of text specific to be able to use that. But for example, for text data, you can do all kinds of, let's say, semantic coherence and metrics like that if you like, but that may not be applicable in all other scenarios. Now, RMSE is nice because it's kind of a general simple metric that is about predictive performance on held out data. So that's why we used it here. But I definitely agree that in particular applications, there may be other metrics that are of great interest. So it's kind of it depends on what domain we are going towards.
Okay, thank you very much.
Thank you.
Okay, thank you. And then we have a question in the chat by Lydia Pivovarova. And she's asking, how does this work comparing to structured topic modeling? For example, topics over time, dynamic topic modeling, and so on.
We actually, I think we had a comparison to DTM, so the dynamic topic models. That is one of our comparison methods here. So you can see that it's not as good, right? And JPP is another method that tries to do this, taking into account dynamics. Obviously, there are some others as well. So I don't mean to say that we compare to every single possible variant. So in our paper, we talk about some approaches that I couldn't cover here, but generally speaking, there are many approaches where there are limitations. For example, some of them are limited to integer data. I mentioned that, for example. So there are some approaches based on Poisson processes, for example, that may have this kind of limitation, whereas not all real data have that characteristic. So we wouldn't like to deal with that limitation. I think that I don't want to, you mentioned one particular method, so I think we didn't compare to that one yet, but I don't remember whether we considered it theoretically in the paper. I'd have to check back basically. So maybe we can, I can return to that if it's important to you. But generally speaking, we found that at least at the time of publication, most methods had this problem that they couldn't take into account both dynamics and multiple sources, or they had other restrictions like this integer data only.
Thanks.
Thank
you very much.
Okay, thank you. So still, I guess we have time for one or two questions if there are such.
So here is Matti, can you hear me?
Yes, we do. Please go ahead.
It's about the first presentation. So, well, I have a multi-label classification problem, and I was kind of thinking, how would you position the method, you know, with multi-label classification? How would it be applicable to that? Well, that's my question.
Well, the whole idea is that you want to be able to have a method that in a low dimensional space represents the separation of classes as it is in the high dimensional space, so that you don't want to overlap classes where they shouldn't be overlapping, but you also don't want to stretch apart some data points where they actually should be overlapping or right next to each other. So we saw that in some of these examples where some other methods like SUMAP, for example, or they made this artificial over separation of mixed together data points. So if you're working with automated later processing methods, then certainly you would want this kind of behavior, because you don't want to train your later processing on data that is artificially separated, for example, or artificially overlapping either, of course. Now the overlap is something that in many methods just comes because you're just reducing the dimensionality, so you have some losses naturally, but in our case, we're just directing the losses. Okay, if you have to have some overlapping, then at least let's try to avoid overlapping between classes.
Right.
So
I think what you say is exactly what I want. So is this somehow available somewhere if I want to try it out?
hold on. I think we definitely have code. I don't remember whether we yet published that or not, but basically get in contact with me and I'm sure that we can provide access to it's we are all about sharing this and we want people to start to use it. I don't know if we have a repository up right now, but I'll check back. I have to say that I didn't implement this now myself. This was my colleagues who did this, so they would have the code access, but I can definitely check with them whether they have that already available somewhere.
Thanks.
So great, thank you for the great presentation, Jaakko. And we are now at the end of the seminar for today. So thank you for the speaker and for all audience, and thank you for the good discussion also afterwards. And I will see you all at the next week's seminar then again.